So from here we get UZR is just equal to dP dz over 4 mu r squared over r squared. What will be the Umax? The Umax will be at r equals to 0, right? Minus 4 mu over 1 dP dz r squared. Only in the middle axis, only in the axis, will we have the least influence from the boundary of the pipe, right? And how to interpret the minus sign? If dP dz is a negative value, then the pressure here will be a proportion, right? If dP dz is a negative value, that means the pressure here is bigger than the pressure here, right? And this thing is has a minus sign, and which cancels out with this minus sign, and we'll get a positive value for the velocity. Okay, so another thing. Oh yeah, if we plug this into the UZ, what do we get? We get another way to write the UZ, right? It's just something like this: Umax times 1 over 1 minus r squared over r squared, something like this. Okay, so if we calculate the average velocity, we also need to do an integral, right? So what's the shape of this profile? Remember, now we are in a 3D world, right? This is a round pipe. So actually here we have a paraboloid, right? Paraboloid. You can do the integral. It's not something very hard to do. You can do something like this. You take out a ring, and what's the area of the ring? Let's suppose this length, the thickness of the ring is dr. This thing is dr. So the area will be 2 pi r dr, right? Let's suppose the radius here is r. 2 pi r dr. And we times the u, and we integrate from 0 to r, let's say. So it may be something like this. But I'll tell you the result, because we are engineers, right? The result is very simple. Do you remember the result, the average velocity for a parabola? It will be 2/3 of the max velocity, right? Here in a paraboloid, the average velocity will be 1/2 of the max velocity. This thing will be just 1/2 of the max velocity. Of course, you are welcome to check the 1/2 by doing the integral, okay? So another thing, dP dz. Let's say the pressure, if the pressure changes linearly with the z direction, so we can just take out the pressure difference, right? Let's say the pressure here is bigger than the pressure here by an amount of delta P. Then delta P over L is just dP over dz. Let's suppose the length of the pipe is L. So what will be the tau Rz? Tau Rz, according to the formula, I'm calculating the shear stress, right? So it's something like this. dz is equal to 0, right? Or you can say we do not have UR. So only this thing is left. And this thing, if we calculate from our velocity profile, you will get this result. So if we calculate the net force acting on our fluids here, okay? What are the forces acting on our fluids? It's just the pressure and the shear stress from the pipe. Okay, now we can call the stress to be tau W, which is tau wall, right? The pressure on the wall, on the boundary. So Fj, if we write the net force acting on the fluids here in the index notation, then it will be something like this: sigma ij ni ds. So if we calculate the net force, first we have delta P over L, I mean this thing, right? Delta P over L. And we should do what? First, we need to calculate the force acting on a ring, right? So we need to times 2 pi r. And then we need to multiply by the length of the pipe to get the total shear force. So we need to multiply by L. So this is the force resulting from shear stress, right? It should have a minus sign. And then we have the proportion of the pressure, which is delta P over L. Delta P over L times the area, right? The area, pi r squared. So what will this thing give us? Pi r squared, oh no, I should also times L, right? I should also, and here when calculating the tau wall, I should use R equals to R. Here I need to multiply by L because the pressure difference between here and here should be delta P over L, but times the length L, right? So what will be my final result? Pi r squared delta P minus pi r squared delta P, right? So this thing will give us 0, which means our fluid is in equilibrium, which is reasonable.